points of intersection where they are intersecting actually. So if you want to compute now area, what you need to do? So we have this beautiful simple formula that, okay, if you want to compute the area between two curves, you need to integrate from A to B the function f of x minus g of x, okay, dx, where this A to B is limit on x. So in this region, what is the limit on x? So this region starts from x equal to 0 and it ends at x equal to 1 actually. Okay, so this is x equal to 0 and this is x equal to 1 as you see the point of intersection. So once they are meeting at x equal to 0, another they are meeting at x equal to 1 actually. So that's what the domain of x is. So you're going to say, okay, let's substitute say 0 and 1. F of x is upper function. So what is the upper function? The upper function is really this 2x minus x squared. Okay? 2x minus x squared minus, and what is this? You know, the lower function, the curve the lower curve, so it is really x squared and dx. And then simply integrate this function. We know that we can integrate it as 2x squared by 2. This will become 2x squared. So this is going to be 2x cubed upon 3 and then substitute 0 to 1. So when you're going to substitute 1, you're going to get 1 minus 2/3. Okay? And minus, when you're going to substitute the lower limit, you're going to get 0 minus 0. So the area is really 1/2 units. So this is 1/2 square units. Not 1/2, but 1/3 square. Okay? 1/3 square units. Okay? So you see that if you know the two curves, okay, and you want to find the area between them, so either the limits will be kind of known to you, or if the limits are not known to you, that okay, you want to compute the area from where to where, okay, you can compute the area. Yeah, you can find first the limit by computing the point of intersection of both curves actually, and then compute the limit. Okay, then compute the limit. All right. What would be the interpretation of, say for example, I want to physically interpret the area between two curves. Okay? So can area between two curves have some kind of physical interpretation? The answer is, why not? If the definite integral has some kind of physical interpretation, then why cannot the area between two curves have a physical interpretation? So imagine you are computing the velocity from instant t1 to instant t2. Okay? We are computing the integral of the velocity from the instant t1 to t2. What would be the meaning of this integral? That okay, this is my time axis, this is my velocity axis, so I have a velocity curve. So this is my, velocity, okay? And the area under this velocity curve is basically representing what? So it is representing what? We know, and we saw it previously, that by fundamental theorem of calculus, I can say that since the velocity is t1 divided by t2, so this is going to be ds by dt, the change in displacement with respect to time, okay, is velocity. So when you compute this, you're going to get s of t2 minus s of t1. In other words, this is representing the integral between the integral of the velocity between two instants, say instant t1 and instant T2, okay, is representing what? So mathematically it is representing the area under the curve, but physically it is telling you the net displacement of what you call whatever particle or vehicle or whatever you are talking about between the instant T1 and T2. Okay, so this is really the net distance covered between T1 and T2. Okay. So this is what the interpretation of one curve is. But now imagine you don't have one particle that is moving, but there is another particle that is moving actually, and that has such a velocity curve actually. Okay, that is such a velocity. So for example, this is representing the velocity curve of one vehicle, one car, and this is the velocity curve of another car actually. Now, what would be the meaning of the area between these two velocity curves of the two vehicles? Okay, so what would be the interpretation of the velocity of the integral of the area between these two velocity curves? So let's call this, say this is velocity v1 or velocity of say vehicle A, and this is the velocity of the vehicle B. Then what would be the meaning? Okay, what would be the meaning of this curve? This area. Now I know about the integral of the velocity VA between T1 to T2, so I can say the net displacement, the integral, for example, if I write VA here, this is going to tell me the net displacement, okay, made by the vehicle A between the instant T1 and T2. So what would be the meaning of integral, VB minus VT? So this is the net displacement, okay, the net displacement between made by the vehicle B, okay, vehicle B between the instant T to A. So the area, so this area is going to be the, T1 minus T2, the velocity of the, the velocity of the vehicle A and the velocity of the vehicle B dt. Okay, so I know this. But I can write this as that, okay, this is T1 minus T2, okay, the velocity of the vehicle VA dt minus the velocity of the vehicle B between the instants T1 and T2. And by this interpretation, this is going to tell me the net displacement of vehicle A between the instant T2 and T1, okay, minus the net displacement, okay, between the vehicle B between the instant for vehicle B between the instant T1 and T2. Okay, so SB is representing the displacement of vehicle B and SA is representing the displacement of vehicle B. What would this represent actually? So what would the distance between these two quantities is representing? This is telling you that in the interval A to B, when the both particles were moving, okay, when the both vehicles were moving, what was the distance between the both vehicle for this entire interval T1 to T2? Okay, so we know that when two cars are moving, okay, going in the same direction, for example, the distance between them vary. Okay, the distance between them vary. So if this is representing the net displacement made by vehicle A between instant T1 to T2, and this is representing the net displacement made by the vehicle B between the instant T1 and T2. So this difference is going to tell you what? This is going to tell you that how far the vehicle A and B were away between the instants T1 and T2. Okay? So this tells us the distance, okay, between the net distance between the vehicles A and B between instants T1 and T2. So it's telling you that, okay, if there are two vehicles moving at different velocities, like some vehicles are getting slow, others, for example, getting accelerating. So it's like velocity is increasing and the velocity of vehicle A is slowing down. So the distance between these vehicles would change actually. Now what is that distance between the both vehicles when one is slowing down and other is, for example, moving faster? That distance is going to be basically, or you can interpret that distance as the area under the curve between, what do you call the two velocities, the area between the two velocity curves actually. Okay? So this area between the two velocity curves is giving you the distance. Okay. So, if you have physical situations, you can even maybe interpret the area between curves physically. Okay. Now, imagine a situation. I want to do an interesting example now. So imagine you have been said to compute the area between a line y equal to x minus 1, okay, and y square equal to 2x plus 6, I think. Okay. When you're going to plot these two curves, they are going to look like this. Okay, they are going to look like this. How they are going to look like? They are going to look like this. This y equal to 2x square plus 6 is going to be a parabola like that actually. So it's going to be a parabola like this. Okay, which intersects at some point, which you can compute easily. And what would be y equal to x minus 1? So this is, so y equal to x is line that that goes through the middle, so x minus 1, so it's going to be 1 unit below actually. So it's going to be a line, okay? So it's going to be a line that goes like, what do you call, this actually, okay? Something like this. So this is line y equal to x minus 1. Now if I say you to compute the area between these two curves, okay? Compute the area between these two curves. Now we have a little trouble. Okay? We're going to see that we have a little trouble. And what would be that trouble actually if you want to compute this? You need to split this area into two parts actually. Into these two parts. So it's like first finding the area between this upper nap of the curve and the line, and then you have to find the area between these two parts. So that is going to give you the net area between these two curves actually. From a point of this, if you see this area from say, this perspective, then there are two different kind of regions that you have to deal. Okay? First is this region, which starts from the parabola and ends at line, this line y equal to x minus 1. And the second region is which starts from the parabola and ends at the parabola as well. So you have to, do a strange kind of calculation actually. Okay. So what should be done? So one of the trick in such situation is going to be that rather than doing the area or doing the computation through, for example, this formula, that f of x minus g of x, in other words, doing the computation, okay, doing the computation, what do you call, with respect to the variable x, we can play another trick. And that trick is, how about if I compute the area between this curve and this curve, but by going that way, this way, this way. That way. In other words, it's starting from this curve and ending up at this curve. So in other words, rather than doing the integration with respect to x, how about if we do the integral with respect to y actually? Okay? How about doing the integral with respect to y? We can do it. There is no restriction in it actually. So for doing the integral with respect to y, you have to, for example, first compute the integrals, you have to first compute the value of x in the terms of the y actually. So from this curve, what would be the value of x in the terms of y? So it is going to be y plus 1. Okay? So let's call, so since for example this curve is lower curve, or maybe you can call it, this is the curve on the left, right, and this is the curve on the left actually. No matter how do you deduce it, write it, so this is going to be 1, value of x in the terms of y. And you can also get the value of x in the terms of y from this curve. So what is the value of x that you're going to get from this curve? So you're going to get x equal to, so subtract 6 and divide by 2, so it's going to be y square minus 6 upon 2. Okay? Y square minus 6 upon 2. And then the required area, so let's call this function as the function y, okay, or maybe g, doesn't matter. And let's call this function as function r. Okay, if these are f and g, okay, let's call this function f actually. Doesn't matter. So x is the function of y and x is the function of g actually. So the area now is going to be some function that starts from some point a to b. How to find these points a to b? Okay, let's first find these points a to b actually. Okay, in other words, we need to find the y's in this region. Y starts from where and ends, what do you call where actually? So in this region, y starts from this point and goes up to what do you call this point. And how you can find these points? Just compute the intersection. And how you can compute the intersection actually. So in order to compute the intersection, you need to equate these both equations. So let's do the y plus 1 equal to y square minus 6 upon 2. Okay. So this will become what? 2y plus 2 equal to y square minus 6. And then you can solve this quadratic equation, y square minus 2y, and you have 8 equal to 0. Okay, and then I can, make a factorization of it. Minus 4y plus 2y minus 8 equal to 0. Okay, so therefore you're going to get two values. So this is going to be y minus 4 plus 2, this is going to be y minus 4. Okay. So you're going to get two values. So one value is going to be y equal to negative 2, and the other value is going to be y equal to 4 actually. So you got these two values. So in other words, in our integral, when you want to do, for example, this integral, you know, but in the variable y, in the variable y, then this area is going to be, you know, this area is this integral is going to be integral with respect to y. But y starts from negative 2. The lower value is this, and it goes up to positive 4. Okay. Now, what is this curve? Okay, so this curve is y square equal to 2x minus 1. But what is the value of x on this curve? So, if you want to, for example, substitute, so this is the, you know, really f of y actually. So, you can substitute this y square minus 6 upon 2 minus this line, you know, and this line in the terms of y has this formula, which is y plus 1. Okay, which is y plus 1 and dy. This is what that you're gonna get, and then you can solve this integral and compute its value actually. Okay, compute its value. So when you're gonna compute this value, you will see that you're gonna get 18. Now, making this computation is way easier. So in variable y, making computation is easier than the making the computation in x, because in case of x, you have to, you know, compute the two different areas actually. Okay, you have to compute the two different areas and put them together to compute the area between the curves. While with respect to y, you can directly curve. So sometimes, you know, computing the area between the curves, or even doing integration in general, is easier when you do it in the terms of the y actually.